My name is Michael Cope, and I worked with Ezra Rice to develop the Earthquake Risk Analyzer and completion of the What's Shakin Baby assignment for Dr. Dan Ames at the Brigham Young University GIS software development class. We were required to solve a problem statement using Arcpy within the Python framework. I will discuss the problem statement and our solution to the problem. I will give a brief demo of how the tool works in ArcMap 10.3 and show the results that are produced. Later, Ezra will review the underlying logic in the code. So earthquake intensity impacts areas with greater slopes or elevation changes. We attempt to identify these areas and assign a risk value based on these two variables. We created an ArcMap toolbox that downloads the earthquake data from the USGS website and compares it with the digital elevation model of the area to produce an atlas report of the various historical earthquake events within a desired period of time. The earthquake data was obtained from the USGS Earthquake Hazards Program website. During development of this tool, the USGS began changing the older raw data to a new format that is not supported with the tool that we created. So you can see here, as you go and click on the text file, it lets you know that it's in a different format than the one that can be used by the tool. However, so because of this, we collected data for the years 2013 to 2016. The data that was received is in a text format that allows us to that we were able to manipulate to create the different ArcMap layers. When the earthquake risk analyzer is opened in ArcMap, the user is presented with a user interface that looks like this. The first parameter is the state, which is a drop-down menu that lists the states that are supported by the tool. Additional states can be added using the USGS codes. The second parameter is the start year, which is the first year during the time period in which the desired events occurred. The year should be entered as 4 digits. The end year is the last year within the time period of interest and is also entered as 4 digits. The output file location is then specified by the user, and the DEM that is desired is also selected. So to recap, we are running this for the state of Utah for the years 2013 to 2016 using a 90-meter DEM. So as you can see in the message modal, information regarding the current state of the tool is printed to the screen.
Okay, so now it's Ezra just for a brief second. We cut out the video just so that we saved some time for you guys. As you can see, the code is finished running and it has taken about 8 minutes and 3 seconds to finish. So that's about how long we can expect a tool like this to run for the 4-year period that we were running it for. So now we're going to go into the PDF and explain a little bit about what the final result is.
Okay, the output of the tool is a single PDF report of the historical events. So here we're just cycling through a few of the different events that occurred. So this particular event occurred on the 14th of March in 2014. The magnitude of the earthquake was 3.2, and the latitude and longitude are also given below in decimal degrees. And the displayed raster describes the risk associated with the historical earthquake event. Areas that are displayed in green to red represent areas of high risk, and areas displayed in white to blue are areas of low risk. Historical events are used to predict the risk of potential property damage if a similar event were to occur in the future.
Okay, now we're getting into the technical details of the code itself. What we've done is imported several of our libraries that we need, and you can see that there's this LXML library is not native to the ArcMap Python interpreter, so we actually had to install that separately, and that can be done using pip install LXML, or you can use it through your favorite IDE. Going on, what we decided to do was create a class for all of our methods, and that lets us create um, class-based variables that we can use throughout each method instead of making global variables. It also allows us to make this code itself very reproducible and portable. So what we've done here in this first section is we're defining all of those variables that we saw in the ArcMap GUI. When you open the toolbox, this section is just reflecting those variables. Moving on, we're creating all of our temporary folders and creating paths to uh, our symbology layer to get that nice color gradient on our rasters. We create a Python object or dictionary called event metadata, where we're storing all of the metadata of each event. So the longitude, latitude, date, and magnitude of each event it's being stored in this class dictionary. We then move on and we define the variables or the environment settings rather. And next we're checking to see if these temporary folders or file paths exist. If they already exist, then we're not going to create them. If they don't exist, then we do create them. Then we establish what our PDF template is, as well as our final output document. So our first method that we call is collect data, and the input parameter for this is the event year. And let me just scroll down real quick to the bottom so that you can see how that works. What we're doing is we initialize this class on this line, and then we take a loop with the range of the start year going through the end year plus 1. Because it's a for loop, we want to add that additional year so that it actually runs the desired last year. So, and then within that loop, we're calling collect data and giving it the year that we're currently processing. So back to the method, we create a list of event IDs. We create the URL to that USGS website that we showed. What we're doing here is using the library urllib2 to basically read and process the web page at this URL that we've defined. And then what we go through and do is actually do our own custom filtering because the website doesn't do a lot of filtering properly. You'll click on Utah and sometimes you'll get an event in Wyoming. So we're doing some custom filtering after that in this section of code. Moving on, we create a temporary directory. Actually, we've already created the temporary directory. What we're doing is just checking to make sure it exists. And then moving on, we're doing for event in that list that we've created, we're downloading the zip file, unpackaging it into the temp directory, and then what we're doing is we're renaming each of the grid XYZ files that's found in that zip file to be the event ID.xyz so that we don't get duplicates or overwriting errors. We let the operating system catch up. Sometimes it just needs a little buffer. And then we remove the zip files or the zip directories because we're done with them. We don't need them anymore. So that's the completion of collecting the data from the USGS website. Now what we want to do is convert the XYZ text file into a CSV file. And we do that using the CSV library that we import. And what we do is we get a hold of that raw data, that XYZ file. And then what we're doing is we create a CSV file and we write our header to the first line in the CSV file. And then we look at our text file right here in this if first line. We're reading the first line of our text file and storing all of that metadata that we want into the event metadata dictionary. And then after that, what we do is for every line in the text file after that, we're writing it to the CSV file, converting the spaces to commas. And then we save the CSV file using this bit of code right here. And this is where all of the lines are actually written. So this just creates a line buffer, and then we write them here. So the next method in our process is actually called Geo Processed Data. So this is where we take the data from the CSV file and convert it into our layers and rasters and run that whole analysis so that we get the pretty layer that we saw on the atlas. So what we're doing here is we create a slope raster using the DEM that we've defined, and we save that. We're going to use that in raster multiplication. Then what we're doing is we go through every CSV file in our raw data directory, so every CSV file that we created, and we create a layer for it using this make XY event layer management tool that's in the Arcpy package. And its inputs are basically the input table, the X column, the Y column, your output layer that you want it to be, and you can specify a projection. We specified the WGS 1984 projection because that is the original projection of our raw data. Then what we do is we do this inverse distance weighted tool to create another raster, and we use that with our event ID so that we go from a layer to a raster so that we can do this raster multiplication. Then what we're doing is we're clipping our slope raster down to the size of our event raster that we just created so that we don't get extra extents that have null values. Then we do our raster multiplication and we save it as a new raster. Okay, I need to speed through this. So we're going to generate the atlas. We define the map document, define the data frame that we're adding the layers to. We define our layer that we want to add, and then an extent layer, which is a little different from the intensity layer that we've created, so that we can zoom to the correct extents. And then what we do is we apply the symbology to the visible layer that we're wanting to look at. And then we add those layers to our data frame. Next, what we do is we select our layers. So we select that extent layer that we just added, and we set the data frame extent to the selected extent. And we refresh the pane, turn off all of the layers that we don't want to see at the moment, and then we update all of the metadata on the template to match the event metadata. And then we refresh again so that it updates, and we save the temporary PDF here, and we append to our final PDF.